Here's a problem that really tests your data structure instincts. Group anagrams. This Pattern Mastery 100 favorite pops up at Google, Meta, and Amazon, challenging you to group together words that are rearrangements of each other. As shown in the image, we're not just checking 2 words, we're clustering a whole list. If you master this, you'll show interviewers that you can go beyond pairwise logic and handle real-world data grouping. Let's dive in. Here's the challenge. Given an array of strings, group the anagrams together. Anagrams have the same letters in a different order, so EAT and T are anagrams, as are TAN and ANT. As shown in the image, the output should be a list of lists, with each group containing words that are anagrams of each other. What's tricky? A brute force way would be to check every word against every other, ON squared comparisons. That's slow. The real trick is to find a unique signature for each group, so you can collect them in ON time. The easiest way? Sort each word alphabetically and use that as a hash map key. Every anagram will have the same sorted form. Here's the plan. Create a hash map dictionary to group words by their sorted signature. For each word, sort its letters to get the signature key. Add the word to the group in the hash map with this key. At the end, return all the grouped values as a list. Now, let's break down the first Python solution for group anagrams, a simple and intuitive approach that groups words by their shared letter patterns. We start by defining a solution class. This is the standard structure LeetCode uses to run your code. This defines our main function. It receives a list of strings, and our job is to group together all words that are anagrams of each other. Here we create an empty dictionary called groups. Think of this as labeled buckets where each key represents a group of anagrams, and each bucket stores all the strings that belong together. We loop through every word in the list. One by one, we're going to figure out which bucket that word belongs in. This is the clever part. We sort the letters of the word S, and that sorted version becomes the signature of the anagram group. For example, both EAT and T become EAT. Creating this key requires sorting, so this part contributes to the ONK log K time complexity. We check whether this signature already exists in our dictionary. If the bucket doesn't yet exist, we create a brand new empty bucket for this anagram pattern. Now we add the current word S to its matching bucket. Words with the same sorted signature are grouped together automatically. Finally, we return all the buckets as a list. Each inner list contains one full group of anagrams. And that's how this algorithm works. It first builds a dictionary to store groups, then uses a sorted version of each word to place it into the right group. Efficient, simple, and elegant. Test case check. Let's walk through it. Input strs equals EAT, T, TAN, 8, NAT, BAT. Let's test our function using this input array. EAT, T, TAN, 8, NAT, BAT. These strings represent a list of words, and our goal is to group the anagrams, words that contain the exact same letters but in different orders. Quick logic check. To group anagrams, we sort the characters of each word. EAT, T, and 8 all become EAT. They go in the same group. TAN and NAT both become ANT. They form another group. BAT becomes ABT, stands alone in its own group. So we expect 3 groups total. Output: TAN, NAT, BAT, EAT, T, 8, and that's exactly what our program outputs, neatly grouped sets of anagrams. Even though the order of groups can vary, the content matches the expected result. Expected: BAT, NAT, TAN, 8, EAT, T. Your output: TAN, NAT, BAT, EAT, T, 8. Everything lines up correctly. Same groups, same words. So, our implementation is correct. The algorithm accurately groups all anagrams by using their sorted signatures, clean, efficient, and fully validated by the test case. We begin by defining the solution class, the structure LeetCode looks into to run our method. This defines our function. It receives a list of strings and must group together all words that are anagrams of each other. We create an empty dictionary called groups. This will map a unique signature, our character count key, to a list of all anagrams that share that signature. We loop through each string in the input. Every word will be analyzed and placed into its matching anagram group. We build a 26-element list representing the frequency of each letter from A to Z. This becomes the key idea behind solution 2, transforming each string into a fixed size signature, making grouping fast and efficient. This keeps our solution at on middle.k time, where n is the number of strings and k is the average length. We now scan through each character in the current string. This increments the bucket that corresponds to the letter ch. By converting the character to an index, we ensure accurate tracking of all letters. We convert the list into a tuple so it becomes hashable and can be used as a dictionary key. This tuple uniquely represents how many of each letter appear in the word, meaning all true anagrams share exactly the same key. If this signature hasn't been seen before, we create a new group for it. We initialize an empty list to store all words belonging to this anagram group. Then we add the current word to its matching group. Finally, we return a list of all grouped anagrams, and that's how this algorithm works. It first builds a fixed size character count signature for each word, then groups words that share the same signature. Efficient, simple, and elegant. Let's test our function using this input. Eat, tea, tan, ate, nat, bat. These strings represent a list of words, and our goal is to group together all the words that are anagrams of each other, meaning they use the exact same letters, just rearranged. Here's why the solution works. The algorithm groups words by a common key, usually the sorted version of the word. For example, eat, tea, and ate all sort to eat, they belong in the same group. Tan and nat both sort to ant, they form another group. Bat sorts to abt, it stands alone in its own group. So we end up with 3 valid anagram groups. And that's exactly what our program outputs. Eat, tea, ate, bat, tan, nat. This matches the expected groups. Bat, nat, tan, ate, eat, tea. The order of the groups and the order of words inside each group doesn't matter, as long as the anagram sets are correct, and they are. So, our implementation is correct. The algorithm successfully groups all anagrams that share the same character multiset, efficient, accurate, and reliable. The big takeaway? When solving problems like this, stop comparing, start categorizing. By identifying unique signatures for patterns, you not only improve efficiency but also show interviewers that you think like a true problem solver. Have you ever noticed how some problems test not just your logic, but your data structure instincts? That's exactly what group anagrams does. One of those interview favorites that shows whether you can move from pairwise logic to true data grouping. We were asked to take a list of words and group together all those that are anagrams, words made up of the same letters, just in different orders. Essentially, it's about finding clusters of rearranged words efficiently. A brute force approach would compare every word against every other, (n² time, which is way too slow. Instead, we looked for a smarter way, giving each group a unique signature by sorting the letters inside each word. That becomes our hash map key, and every anagram naturally falls into its matching group. We looped through the list, sorted each word alphabetically, and used that sorted version as the key in a hash map. Each time, we simply added the original word to its corresponding group. By the end, each key represented one group of anagrams. Implement recap. We then ran this logic step by step in LeetCode. No syntax issues, no edge case surprises. The grouping worked perfectly. After running through the test cases, every input matched the expected output, confirming that the hash map method grouped all anagrams correctly and efficiently.